All right, welcome to part 5 of this review. In this video, I'm going to talk about the uniform distribution and the normal distribution. These are two different distributions for continuous random variables. So a continuous random variable is one that can assume any value in an interval on the real line or in a collection of intervals. So with discrete random variables, they take on a limited number of potential values. These would be integers. Whereas with continuous random variables, they're not constrained to be integers. We could have something like 11.7. So if we were counting how many cars are sold, we would go to 11, then the next value would be 12. But if the variable is continuous, it's not constrained to be 11 or 12. So for example, you could have 11.7 pounds of something, or 11.7 inches, something like this. So the probability of the random variable assuming a particular value is going to be 0. That's a characteristic of this kind of distribution because essentially there are so many different possibilities that the probability of it taking on any one particular value is 0. Now think about this if we're considering options of 11, 12, 13, versus something between 11 and 13, there are an infinite number of possibilities between 11 and 13, right? 11.01, 11.001, and so on. It's just an unlimited number. Then the probability of the random variable taking on a value within some interval is what really becomes interesting, because the probability of being any particular value is 0, so we might be more curious about the probability that the value lands between something. So if these were dollars, let's say this is the cost of something, what's the probability that the cost would be between $3 and $11.70, something along those lines. Now, the probability of the random variable being a value within an interval, say from x1 to x2, in the previous example, x1 would have been 3 and x2 would have been 11.7. That's the area under the graph of something called a probability density function. So the graphs here show a kind of probability density function for both the uniform and the normal distribution. The uniform distribution, as you see over here, it looks quite rectangular, whereas the normal distribution has this kind of bell-shaped appearance, right, that we see here. So they're different, and they're both continuous, and these representations here show the probability density functions. Now, if the random variable is uniformly distributed, what we're seeing there is that the probability is going to be proportional to the interval's length, right? So the interval between x1 and x2, how long is that interval? And then the probability will be proportional then to the overall length from the smallest value to the largest value. So in this distribution, what we have is a formula that tells us the probability, and you can see that here. So we have the probability that x is between x1 and x2 can simply be written as x2 minus x1 over b minus a. So what are b and a? So a is the smallest value the variable can assume, so it has some lower limit, and b is the largest value that the variable can assume, so it's got some kind of upper limit. And it might be hard to think of a lot of examples where a variable has a lower limit and an upper limit, but these things can exist. And then the density function, that probability density function, was this lowercase f here, but in this note here I've got something with an uppercase, this f of x, and we're calling it the cumulative distribution function. That's denoted here with this f. If you're familiar with calculus, then this might make some sense to say that this smaller f here, the lowercase, is the probability density function, is the derivative of the cumulative distribution function. If you're less familiar with calculus, it's not a concern for understanding this concept. Simply you have the function here that is useful in calculating the probabilities. But if you're familiar with calculus, this could be a little more meaningful. So then the expected value is just the lowest value plus the highest potential value divided by 2, so it's just right there in the middle. And then the variance has the formula given there. It's the distance from B to A, or A to B, however you want to look at it, squared divided by 12. I'm not going to go into why that's the formula or how that works, but that is the formula for the variance for a uniform probability distribution when we have a continuous random variable. So let's suppose we have bids on a contract and they're uniformly distributed on some interval. So this might be the case because there's a specified minimum bid, so no bids can come in below a certain value, and there might also be a known maximum, for example, that no one could potentially value this beyond a certain value, certain amount. This could be the case if you're bidding on something, for example, on eBay. Right, there might be a starting bid, and then you might also figure that there isn't going to be a single bid above a certain amount. Maybe people are aware that that could be purchased outside of eBay for that amount. In this example, I'm thinking about bids for a contract. Same kind of deal. You might have a situation where the government is allowing bids on some road work or guard railing, and they might have it known ahead of time that they won't take any bid above a certain amount, so they won't pay more than, in this example, $14 per foot. But then it also might be known pretty well across the industry that it's impossible to have a bid come in at below $10 because it's just the cost. It would be unreasonable to think that a cost could be below $10. And this might be an example. So if we have this setting here, $10 and $14 are the range of values, we can calculate the expected value. We have in this case the value for A, the minimum bid, would be $10. The value for B, the maximum bid, would be $14. We're just splitting those, or taking the middle or average of those, we get 12, and in this case it would be dollars. And then we can figure out the variance as well. So the variance, we have this formula. Maybe this looks a little unusual here, but we just had B minus A squared divided by 12. So in this case, B was the $14, A was the $10. The difference is $4. 4 squared is going to be 16. Then 16 divided by 12 here in the denominator, we get 1.333 as the variance in this example. All right, so in this case, let's suppose we want to find a probability associated with this example. So let's suppose we want to find the probability of a bid being between $12 and $13, again for per linear foot, let's say. So here we can write this out, the probability that X, what is X? X here is going to be the bid. That's what we're meaning here with this. It's between two values, 12 and 13. So those two values come in over here. So 13 becomes like our X sub 2. 12 is our X sub 1. 14 is like our B. And 10 is our A value. So if we were to go back and look at the formula, we would see this there. 12 minus 13 is 1. 14 minus 10 is 4, and that gives us 1/4, or if we want to write it out in decimal form, 0.25 is the probability. So the probability of a particular contractor bidding between $12 and $13 is 0.25 in this example. So I want you to take a moment and give this a little try. You can pause the video after you read this question and then give it a try. So you're bidding on a piece of land against one other bidder, and you expect your competitor's bid to be uniformly distributed with a minimum of $10,000 and a maximum of $15,000. What is the probability you will win with a bid of $13,500? So go ahead and pause the video and try that out, and then come back to see the answer. All right, so hopefully you had here the probability that X, that is the competitor's bid, is less than $13,500. Why? If you bid $13,500, you will win only if the competitor's bid is less than $13,500. And that's what this X is, right? It's the other bid, right? It's not your bid. Your bid is you're going to bid 13,500. All right, so how do we figure this then? No bids are less than 10,000, so you know your competitor is not going to bid below that. So you get the 13,000, that would be like the X2, and the 10,000 would be the X1, because you know they're not going to bid less than that. And then we have over here again the B and the A, and we just crank through that. Get 3,500 over 5,000. That is 0.7. So the probability of winning would be 0.7, or if you were to bid on lots of pieces of land like this, lots of auctions of this nature, and you would bid that amount each time, you would win 70% of the time, roughly. That's what that says. So the area under the graph, the f of x, and probability are identical. They'd be the same thing. So if you were familiar with calculus, which I don't know who's watching this video, so some of you may be and some people may not be, then you may be familiar with calculus and you may be familiar with taking an integral, and that's what you would be looking at. So this is valid for all continuous random variables. The probability that x takes on a value between some lower value x of 1 and some higher value x of 2, that can be found by computing the area under the graph, that f of x, over that interval, so x1 to x2. So that would be done using calculus, for example, is one possibility, or using a computer or calculator. So we have another distribution beyond the uniform distribution that I'm going to address here, and that is the normal probability distribution. So it has characteristics that it's symmetric, and the entire family of normal probability distributions is defined by two parameters, the mean, mu, and the standard deviation, sigma. The highest point on the curve, so that probability density function, is at the mean, which also happens to be the median. The mean can be any numerical value. So it can be negative, it can be 0, or it can be positive. So if you're thinking, how could it be negative? What we might be measuring would be something that does take on negative values. So for example, weight loss, or it could be financial losses. So it could be something that's negative. All right, so some additional characteristics are the standard deviation determines the basic shape of the curve. So larger values result in flatter curves. I'll show a picture here in a moment. And probabilities for the normal random variable are given by areas under the curve. The total area under the curve is 1, and you've got then half, so 0.5 to the left of the mean and 0.5 to the right of the mean. So here's an illustration of different standard deviations and the different basic shapes of the curve. So the basic shape of the curve, hopefully we're in agreement that it looks basically bell-shaped. But we have this example here. It's a basic bell shape. Use this red line here on top of the black. And that has a smaller standard deviation than this other curve here that's also basically bell-shaped, but much flatter, right? So the one that I did first, right, that has the smaller standard deviation. The larger standard deviation here is going to give a flatter looking bell, if you will. Okay, so that's the distinction there, what's meant by having a larger standard deviation and a potentially flatter look to the distribution. So a random variable that has a normal distribution with a mean of 0 and a standard deviation of 1 is said to have a standard normal probability distribution. And for that we use the letter Z to designate that. So that's a fairly standard notation, is Z. We can convert anything that is normal into a standard normal by applying this little function here, or this little equation that you see here. Right, so we can make it Z by taking the value that we're starting with, this x, subtracting off the mean, mu, and dividing through by the standard deviation. So applying that, subtracting off mu, and dividing by the standard deviation, that will give us a Z that is distributed standard normal. Right? So you can think of that simply as the number of standard deviations that your value x is away from the mean mu. That's a way to interpret Z. If a random variable follows the normal distribution, then approximately 68% of the observations are going to have a Z value between -1 and 1. Approximately 95% of observations will have a Z value between -2 and 2. And nearly all observations will have a Z value between -3 and 3. So this is sometimes referred to, or a similar concept, as the empirical rule. The battery life problem. So a company believes that its batteries have a life that is normally distributed. The mean life of a battery is 100 hours with a standard deviation of 15 hours. We've got two questions here. What is the value for a battery that lasts 80 hours? And approximately 16% of batteries will last longer than how many hours? So if we were to pick the top 16% of batteries, how long they last at least how many hours is what that's saying. So here we've got the mean life of a battery is 100 hours with a standard deviation of 15 hours. What is the Z value for a battery that lasts 80 hours? All we're doing here is plugging in the values given the formula. So the formula was x minus mu divided by sigma, the standard deviation. So we're just pulling in these values, right? 80 is our value for x. 100 is the mean, our value for mu. And 15 over here is the standard deviation. That's the value that goes in the denominator. So 80 minus 100 gives us -20. 15 is the standard deviation. Divide -20 by 15, we get -1.3333, and the 3 is going to repeat. Now here, notice that if the value, your x, in this case 80, is less than the mean, you're always going to get a Z value that's negative, which is what happened in this case. It's negative. So negative Z value means the value is below the mean. Now another question that was asked there is approximately 16% of batteries will last longer than how many hours? So here we're going to go back to that empirical rule idea. In this case, approximately 68% of batteries last within one standard deviation of the mean. So that means we're going to have 32% that are outside of that range. So if I draw this here, I've got my normal curve here, and I'm going to have here 68%. That means that over here plus over here, I'm going to have a total of 32. How do I get 32? I get 16 down below, and I get 16 up above, 16 over here, and those add up to this 32. So I get 16% that lasts less than one standard deviation below, so this 16% is over here, and I get 16% that lasts more than one standard deviation above. That 16% is up here at the top. Okay, so that's how this looks, where I'm coming up with these two values, 16%, 16%. So then I say the mean life of a battery is 100 hours with a standard deviation of 15 hours. Approximately 16% of batteries will last longer than how many hours? Well, one standard deviation above the mean is where I get this 16% from. So 100 plus 15 is 115. So approximately 16% of batteries are going to last longer than 115 hours.